Okay, can you see my screen?
Yes.
Okay, all right. So we go on. Um, I think we left at this heterodyning. Let's see. Oh, but are there any questions from last time? Maybe I should start there. All right. There's total silence. So we'll go on. I remember telling you about this diagram. That all it's doing is just summarizing for us what happens when you have amplitude modulation. The plot is really a plot in time. So the axis that goes at a slight angle going from the back to the front of the screen is the time axis, and the one that is going from the left to the right, almost inside the screen, is the frequency axis. And so you'll find that the lower frequency is on the left. The next is the slightly higher frequency, which is the lower sideband of the modulated signal. And after that, you have the carrier, which is in some bluish gray, so bluish green. And then finally, at the other end, is the higher frequency, which is the upper sideband. Um, okay, so there was this example here where we're having a standard AM broadcast station is allowed to transmit frequencies up to 5 kilohertz. This That actually is what they do. The frequencies are up to 5 kilohertz. The message is up to 5 kilohertz. Um, Therefore, it's going to occupy a bandwidth of 10 kilohertz because you need double that. Um, when you when you have frequencies on the positive frequency axis from 0 to 5, the there is a part of that which hides in the negative frequency axis, and so it actually is double. And you see that when you try to do frequency translation, you take a 5 kilohertz tone and you translate its frequency, let's say by 100, let's say 100 kilohertz, or you'll find that it's going to have two tones, and then you'll be wondering what happens. There will be one at 105, and there will be one at 95. So there's the shifting frequency plus or minus the the message frequency. Okay. Now I think I think we got here. I've not played back my uh, previous videos, but I think we got to this point where we're trying to justify the reason for including the carrier in an amplitude modulated signal. And I'll go down, and then I'll come back to this. The reason why we want to include the carrier is the excuse to use this circuit. This simple circuit, which is called an envelope detector, figure 2.6, which is just a diode, a resistor, and a capacitor. Um, it would actually have been nice if we could put this on a breadboard and display the signals on an oscilloscope. Um, but nonetheless, what it does, and we'll explain this later, but you can just see that when you have a signal that goes up in amplitude and then goes down and then finally becomes negative and so on. What will happen is that on the positive side of uh, we say the positive excursions, when the signal undergoes a positive excursion, the diode will be forward biased, and so it's going to be conducting, and so the output of this in this diagram, the output v0 or v0 will be equal to the input. We're assuming that there's no voltage drop across the diode, or you ignore the voltage drop across the diode. So um, the output is directly connected to the input. When the during the positive excursion. And that time, the capacitor gets charged. Hopefully, if the values are chosen properly, then the capacitor will be charged uh, to the value of the incoming voltage. So you can see that there the capacitor will be trying to reach that. So when immediately the input becomes negative, then the diode will go off. So there will be no longer any um, connection between the input and the output. And so the capacitor will still have its charge. The charge will not go off immediately. So the charge in the capacitor will now try to dissipate. And it will therefore discharge through the resistor and will be discharging slowly. So the net effect is that the the previous value of the output is sort of maintained in the capacitor slightly as it's trying to discharge. And before it discharges completely, the next peak comes, and so on. So this is what's um, making the output follow the so-called envelope, if you like, of the input. And we want to use this to basically follow the envelope. So I'll go back. We will explain this a little bit more later on. I don't expect that the explanation I've given is sufficient for an understanding of how this thing works. But it's basically that you allow the capacitor to charge, and then it will discharge slowly. And by doing that, it will tend to follow the outline of the input signal, which we are calling the envelope. So we'll go back to the reason for including the carrier. So this is so in here. The suppressed carrier modulation, or rather, in the suppressed carrier modulation, you will find that the envelope. I don't know whether you know what the envelope is, but let's look at this diagram. There's a diagram where we are saying example mt equals cos 2 pi f0 t, and you can see that there are some parts where the signal, the amplitude is high, and there are parts where the amplitude is down. So it's sort of so when the amplitude is down, but it's not crossing. The positive peaks, the positive side. If you took um, a signal that just touches the peaks on the positive side, and then the signal that touches the bottom, they don't cross. That is good. If you that's good. That can work when you try to apply that to the so-called envelope detector that I just described below, because the envelope detector will try to follow just the outline, and you get to a point where you have um, the one I just described is said to have an amplitude modulation index of 0.5. In other words, you're only putting about 50% of the carrier, the frequency. So then, if you have what is called 100% modulation, the modulation index is 100% or 1, then the signal will just touch zero. At the lowest point, it's just going to touch zero. Theoretically, you can still use the envelope detector on this one, but I'll tell you why it's risky to do this, because you can't really be sure numerically that when you apply when you let this signal run, that it is just going to touch zero and then start going up. It may cross slightly, so there could be some error. Theoretically, you can have this, but I think it is safer to maybe allow perhaps 99% or something that's not quite 100% for it to work. All right, you could have what is called an overmodulation, where the modulation index is high, and you can see this the third diagram there, where the part that was supposed to be positive sort of crosses to the other side. And so in this diagram, you were telling me the other time that you are not seeing my cursor. I don't know whether it's the same story right now, because I would have been pointing. But anyway, you have the three diagrams. One is marked as 50%, the other one is 100%, and then the third one is over modulation when the modulation index is larger than 1. In this example, it's 150, or 1.5, 150% or 1.5. And so here, this is a case of modulation. You've got too much modulation in here so that the envelope, that outline, crosses the axis. And so if you are to use an envelope detector, what it will do, it will still give you a result, but what it will give you is not the envelope. It's going to be confused. Let's look at this diagram here. What the envelope detector will give you is I think I'll just point to this diagram. Sorry, where we're putting this observation at 150%. The outline is on the positive side only. Will go up, and then at the zero crossing, you start going up again. So because the envelope detector doesn't give you a negative output, it will only give you an output. It's like you're getting a full wave rectified output. So it will go up as the envelope is going up. Then when it hits zero, it starts going up again, but this time will go up slightly, then back to zero, and then up. So the envelope will not be what you want, because what we want would have been that the envelope would have, the signal would have gone down, crossed zero, and then gone up. But the envelope detector doesn't do it. So that happens when you have too much modulation. But if you have just the right amount of modulation, where the envelope does not cross the axis, going negative, then the envelope detector will work. And so the case where we had 50% modulation, there it will work. 100% theoretically it can work, but practically there may be problems. Why this thing does not work when you have the earlier signal, which we call the double sideband surplus carrier, is, I think I should have the diagram for that. Let me see. I hope I did. Yeah. In figure 2.5C, figure 2.5C, you can see the dotted outline. This is the double sideband suppressed carrier signal. The dotted outline is the modulating signal. The dotted outline, which is red. So it starts up and from the positive side, and it crosses down and up and so forth. So what happens? Let me see. Let me show you. The modulating signal is this signal in 2.5b. That's the one you use to multiply with the carrier. Yeah. You take the carrier which is in A, you multiply by the modulating signal. The modulating signal is the signal that carries the message. And when you multiply those two, you get the signal in C, 2.5C. But now you can see that the outline carries our signal there. The scales are not the same, so it's not you're not seeing that the dashed signal is going and crossing down to the negative side and then coming up and so forth. That if you follow from the top to the bottom and then to the top and so forth, that that dashed outline is indeed this should be the same as the one in 2.5b. If you used an envelope detector with this signal, the envelope detector will give you a signal that goes down up to zero, then immediately starts coming up. And so you're going to get a full wave rectified version of 2.5b. The negatives will be flipped to become positive, but that's not what you want. What you want is something smooth that goes gently down and then up and so on. If we put a carrier in here, then we get we get something like this 2.5 D. And because here the envelope does not cross the axis, and so here the envelope detector will work. So in what is called the conventional amplitude modulated signal or system, this is what is referred to, and in that the amplitude, the envelope, which is the outline, stays on one side. I mean, it does not cross the axis. So in this diagram, the envelope detector will just pick the positive side of that outline as the output. So that is the reason for including the carrier, so that the envelope detector, which is very simple, can be used. So you won't have an excuse to use the envelope detector that is very, very simple, then you would have to include the carrier. The problem now is that you have included the carrier, and so it's going to consume some resources because it takes some of the power that you're supposed to use to transmit a message. That power now is going to be put in the carrier. So uh, it may not consume bandwidth because the carrier is just a point in the frequency axis. So you can say a point is dimensionless. I mean, does not have a width, so it does not consume a bandwidth, but it consumes power because the power has to be in the um, in that carrier. So we were saying then that yes, you put the carrier, but there are some disadvantages. You can use this simple circuit. There are disadvantages to the extent that we will find that the efficiency of the message carrying efficiency of an amplitude modulated signal when you have a carrier is actually 33%, one third. We'll see that shortly. All right, so this envelope detector requires the modulation index, MA, and my apologies, I use MA here. Somewhere I've used M, and so it can be confusing, but the context will make it clear. The modulation index, which is the amount of message that you're putting in the carrier, is supposed to be between 0 and 1. If it is 0, then of course you have just the carrier. There's no modulation. And if it is 1, then theoretically the envelope detector can work. But I'm saying practically it may be that you think that you're just touching 0 and crossing and going back, but the signal may slightly cross 0, and there could be some errors. All right. The value of the capacitor has to be chosen properly to give a fast enough charge time and a fast enough discharge time. Or I think is it a fast enough discharge time? Yeah, you don't want the capacitor to discharge too slowly, because if it discharges too slowly, there'll be trouble. So both of them, have to be fast. So the fast discharge is required so that the capacitor voltage reaches the peak of the AM signal during its positive excursions. The fast discharge is required to ensure that the problem of diagonal clipping, which I'm going to explain shortly, does not occur. The most commonly used expression for the value of the capacitor is this expression in equation 2.7. I think I've derived it later on in these notes, and I will let you just read the derivation because it's straightforward. Okay, the diagram that you have here, which I have not labeled, I've not given a caption, unfortunately, is showing three cases. One case is where the time constant in that envelope detector. Remember, the envelope detector has got a diode and a resistor and a capacitor in parallel. But during the time that the capacitor is discharging, it's discharging through the resistor. So it's at that time temporarily the capacitor and the resistor will be in series with each other because the diode part at that time is off. Let me go back to it. In this diagram here, figure 2.6, when during the time that the capacitor is discharging, the diode is off. So it's like that part of the circuit does not exist. You can basically remove that temporarily, and then you'll be having the path, the discharge path is through the resistor. So you have the diode, the capacitor discharging through the resistor, and therefore the time constant is that of the product of the capacitance and the resistor. When the time constant is just good enough, then the output is still a bit rough, but it more or less follows the outline of a signal. This is a general signal. Remember, the diagram that we had previously is for a single tone modulation, but general signals would not necessarily be single tone. You could have a general signal such as the one that we are trying to show here, which goes up and goes down, slightly goes up, and so on. So the output is sort of looking like a sawtooth, but you can, if you don't want this, then what you can do is you can have a simple low pass filter to smoothen that outline. But usually, when you take this envelope detector and you apply it to an AM signal, you will find that you can actually hear the output reasonably well. The ears can hear. The ears will do the low pass filtering, so that you don't hear those spikes. If you like, you say that those spikes will not cut the ear. They'll be smoothened out. All right. Then you get to a point where you have the so-called diagonal clipping, where the capacitor is discharging too slowly. I hope you're seeing the middle diagram, the middle figure in the diagram is a case where the discharge time is too slow, so it's too long. So the value of the capacitor voltage, which is the output, stays up, and there are some peaks that it now misses, because there are some peaks that are below that can't be detected by this thing, and so the output that you get is something else. If you have the third part is where the capacitor discharges too fast, the discharge time is too short. So before the next peak comes, the capacitor is discharged almost to zero, and so on. So you have a very rough sawtooth, signal that is a bit too far from what you want. It's better than the one before it in that the peaks are not missed, but it's bad enough because it tends to go to zero in between the peaks. So what you want is to make sure that the capacitor voltage is just the capacitor value, the capacitance is just right, and that the first diagram that's the job. Okay. But that formula is useful. I think the only thing that needs to be explained here is that the FM max is the maximum frequency in the modulating signal. The reason we're doing that is that you may have a signal that has got several frequencies in it, from the lowest to some maximum value. So we use the maximum frequency in the signal for these calculations. And in the examples that you may have to deal with, you'll be using single tone signals. I think, or if it is a signal that has got several frequencies, the maximum will be given. The resistance value, I think, will pick a reasonable value, 2.2 kilo ohms or 4.7 kilo ohms or whatever, some typical value of resistor that people use. you can use that. So what you do if you are trying to design the circuit is it would be to pick a resistor, and then knowing the frequency, try to do this calculation, and you see if the value of the capacitor that you get is reasonable. Then if not, you pick another value of the resistor, and so on until you get a reasonable value. I mean, you don't want to put a huge capacitor there that is maybe 1,000 microfarads. That's too big. So you'll if you can get the capacitance in some perhaps nanofarads or picofarads, that would be good enough. But this is the formula that you use. So we have here an example which is talking about an envelope detector used to detect or demodulate an AM signal. Look, when you hear me, you will hear me say detect, where this demodulate. We're using the two interchangeably. So when the envelope is decreasing, the capacitor must discharge fast enough. This is what I said there, between the carrier peaks, so as not to miss the next carrier peak. At a point T0, the T0 corresponding to a carrier peak, the capacitor has just reached its full charge, V0, equal to the level of the carrier peak. So you are then supposed to determine the slope of the capacitor voltage at that instant T0, determine the slope of the envelope at the same time T0, so on. This part is it's the part I was saying I'm going to skip because it's reasonably straightforward. I've derived that expression. In other words, we are going on and we're getting to a point where we are taking some derivatives, and we're saying that the derivative of the envelope detector should just equal the derivative of the capacitor voltage. And when you do that, then you go through, you'll get the equation that that we were talking about earlier on, and it is there. Fortunately, I've not numbered it. But this is the expression to remember. But you can go through the calculations that I've shown there. I think you should read through it, and if something doesn't make sense, you can ask questions. There is another approach here which is not. I would not recommend it. The one in Figure 2.7, where you assume that there is the diode forward resistance is let's say 100. The diode resistance RD is 0. Sorry, it's 100 ohms, and you can model the diode output by a straight line starting from, let's say, 0.6, sorry, 0.3. Okay, some books may say 0.7, and so on. Actually, I don't know why in the diagram I've got 0.3, while there I'm using the diode voltage of 0.7. Oh yeah, okay, yeah, it's fine. It's fine. From 0.3, the kickoff point is 0.3 up to 1 volt. The drop is 0.7. Okay, you can use that, but the trouble is that the results that I get using this approach, I've found them to be usually different from what you get when you follow the other method. This is good if you get the right value. So if you say that you have a diode that has got that kickoff bottom on the horizontal axis in Figure 2.7, where it starts from 0.3 up to, let's say, 1, where we're putting 0.3, perhaps it is something else as opposed to 0.3. So this you can use to get the value of the capacitor. But many times, and as I've seen in many textbooks, we use the other equation. I think it's more reliable because this model of the diode, you'll have to be provided by the manufacturer, and so from the spec sheets you will then have the values of the critical points to use. And if you have the right model for the diode that you're using, this is okay. You can use it. But um, every time that I have had to use it, and then I go to the other one, I have found that the results are not quite the same. But I think that can be reconciled by getting the right figures from the manufacturer of the diode that you have in the diagram. All right, so you can use this, but the preferred method is the other one via the equation that we derived earlier. Okay, so virtues and limitations of amplitude modulation. This is amplitude modulation. The good thing with amplitude modulation is that it's very simple. You just multiply the message signal by the carrier, and if you have to add the carrier, that is fine. It's still straightforward. Straightforward as compared to what? As compared to frequency modulation or even phase modulation. So when we're talking about virtues and limitations, we are comparing in our mind amplitude modulation with the other forms of modulation. They're just two left. The frequency modulation and phase modulation. Of course, you can talk about pulse amplitude modulation. You can talk about pulse position modulation, and so on. Those are other forms of modulation, but I think the main ones are these three: amplitude modulation, phase modulation, and frequency modulation. So the limitations of amplitude modulation are that the amplitude modulation is wasteful of power, especially if you have the carrier inserted in the system. You want to put the carrier so that the envelope detector can work, but the carrier has to carry power, and that power you could have used to carry more message, but you can't because you must have the carrier. Then amplitude modulation is wasteful of bandwidth because, as we'll see later, one sideband is enough to carry all the information that you have in the signal that's carrying the message. One sideband is sufficient, but it carries two sidebands, so half of the bandwidth is wasted. So though it is simple in terms of modulation and simple in terms of demodulation, it's wastes power and it wastes bandwidth. Those are things that are good to remember. Then, so now you ask the question, what can we do? Can we have some ways to improve on these problems? Yes, you can, and you can suppress the carrier. If you suppress the carrier, you will of course retrieve the power that would have been lost, or that would have been consumed by the carrier, and therefore you'll have a double sideband suppressed carrier. You could also, double sideband suppressed carrier. What you pay for that is that the demodulation will become more complicated. But at least you can carry more message when you suppress the carrier, because the power that was consumed in the carrier is now available for carrying the message, and then you pay for it by having a more complicated demodulation. You'll see that later. So you can modify the sidebands of the AM wave or AM signal. Modify the sideband. In other words, you could throw away one sideband completely. We'll see why, even though we can mention that as a possibility, theoretically okay, but it's difficult to do in practice. So, in the most general form, you can have this so-called analytic representation of linear modulation, where if you have a signal S of t, you can write it in terms of a cosine and a sine. You have Si of t, cos 2 pi f ct minus SQ of t sine 2 pi f ct. That's what we wrote earlier on. The amplitude modulated signal could be written like this. And depending on now on how you arrange things, we're not going to pursue this, to a large extent. I'm just pointing out that's a way of representing the amplitude modulated signal, where SI is the in-phase component and SQ is the so-called quadrature component. And so we'll be saying that depending on how you create this component, SI and SQ, it is possible to get either a double sideband suppressed carrier, which we got earlier. We got it earlier just by multiplying our input signal by the carrier, meaning that in that SQ is 0. So if you have if S sub Q is 0, then you just have a double sideband suppressed carrier. Theoretically, even if you have SI 0 and the other one is not 0, it would still be double sideband suppressed carrier. In other words, if you have either the sine part by itself and the other one is missing, or the cosine part by itself, the other one is missing, both of them are double sideband suppressed carrier. What do we mean? What we mean is that if you tried to look at that signal in the frequency domain, in other words, you are asking yourself the question, along the frequency axis, where is the signal? You will find that if you don't have one of them, if either SI is 0 or SQ is 0, then what you end up having is a signal that has got a component above the carrier and a component below the carrier. This double sideband suppressed carrier, similar to what we saw already when you multiplied the message by a carrier. You could have a single sideband, which is good. Single sideband meaning that one of the sideband is retained, and the other one is suppressed, is thrown out. That is called single sideband. And because we said that in the amplitude modulated signal, one sideband is sufficient, keeping one sideband therefore is okay for carrying the message. And so single sideband is okay, but it's very difficult to achieve. And again, we promise to say that to see that a little bit later. It is difficult to achieve single sideband because you'd have to have a filter that knocks off one of the sidebands. So in other words, you'll have to have. Let me see if I have it down here, so that maybe not. Okay, it's not. No, it's not. It's not there. This is the time when, if I was presenting this in class, I would have drawn this on the board. But we don't have that. The people who are going to take this course after you will benefit because we will rectify these problems. In doing this, obtaining a single sideband, what you do is you start off with a double sideband suppressed carrier, and you use a filter to select one of the sidebands. The filter characteristic in frequency, in frequency, will be just like it's a bandpass filter, which has got sharp cutoff frequencies. It turns off just at it turns on at the carrier, and is up one side and 0 on the other side to select one of the sidebands. So the problem is that a filter like that, which has got a sharp cutoff, is impossible to design in practice. You can approximate it, but you cannot design it. So in order to go around that problem of the single sideband carrier requiring a filter with a sharp cutoff, which is impossible, we have another version which is called vestigial sideband, where a small piece of the other sideband is left. This is done in carrying the video signal uh, in television signals. So the video signal on television has got vestigial sideband, meaning that a piece of the other sideband is allowed, but it's allowed in a clever way so that later on as demodulation, it can be the signal can be recovered. So here we are basically okay. So what do we take from here? What we take from here is that we were trying to respond to these problems of amplitude modulation. In other words, the problems are that there's wastefulness of power, and we've tried to solve that by suppressing the carrier. We have not yet discussed how we are going to demodulate the suppressed carrier signal. We'll point out its difficulties and how we go about it. But for the moment, we are now addressing the second part. The amplitude modulation is wasteful of bandwidth because one sideband is sufficient. And in order to respond to that, we are trying to modify the sidebands. And so we're trying to modify the sideband. And so the solutions are these. You can have a double sideband suppressed carrier that will get rid of the carrier, so you can use the power in the carrier to carry a message. Single sideband will deal with the wastefulness of bandwidth, reclaiming the other half of the bandwidth that's being used, but is just repeating what is already in one half of the band. And there are problems with that, and so we resort to vestigial sideband, or we can resort to vestigial sideband in order to make sure that we have practical filters that can be built with practical components. So that's a very good outline of what to expect in amplitude modulation. And so what we have in this table here is the type of modulation on the left column, and then you would have what is called the in-phase component, quadrature component, and then the comments on in the rightmost column. So we're just pointing out. Please do not memorize this. I don't know, I don't know how well you people know me, but I don't want people to stress themselves unnecessarily. Memorizing this is not going to help. If you work on these things, whatever is on the table here will basically settle itself in your mind. But you don't have to memorize this. What you need in an exam, if you happen to need a table like this in an exam, will give you. So what I want people to do is to relax and try to follow the logic, how things fit together. So we don't have to memorize the table. We had that alternative representation of an amplitude modulated signal where there was an SI that we called the in-phase component. That's the second column here. And then there was an SQ, which is the quadrature component in column 3. And so what we're basically doing is that we are trying to list on the left the type of modulation and to see what forms these two components are going to take, the SI and the SQ. When you have double sideband suppressed carrier, we are saying that the SI is M of T and the quadrature component is 0. You could actually swap them if you want. You can put you can put the in-phase component to be 0 and the quadrature component to be M of T. If you'd like to put a minus sign there, you can do, but fine. Then you have what follows ABC. I think there's a problem. Well, yeah, no, it's fine. No, it's okay. Single sideband. If you can have either lower sideband or upper sideband. So the SSB. When you want to have upper sideband, sorry, lower sideband, you have a half M of T, and then there's a half M hat and we're explaining on the right that M hat is the Hilbert transform. I don't know whether you're familiar with the Hilbert transform, but in the notes that you're going to get, it is there. I would just tell you to read. We are not going to use it, but we point out the Hilbert transform basically has got a characteristic in the frequency domain, which is a brick wall. The filter that I was describing, which is difficult to design, is basically just that. It's zero on one side, and it is up on the other side, like a step in the frequency domain. And even though in mathematics we can write a Hilbert transform, in practice it's impossible to build it. You can approximate it, and so on. So when you arrange, you can have um, different different signals there. Now let me see. Vestigial sideband, you can have a lower sideband, and you can have upper sideband. But here now there is 1/2 m of t in the for the in-phase part, and 1/2 m prime of t. It's not a derivative. M prime is the output of some filter that is called a vestigial sideband filter. Some people might call it a quadrature filter. Again, we're not going to design this, but it's the kind of filter that is said to have a vestigial symmetry. Think it will take too long to talk about it. So I just mentioned it. So what are we doing here? We are saying that there are ways of getting the various types of modulation signals. And so you can either have double sideband suppressed carrier, and of course these are the forms that don't have a carrier in them. So you can then have single sideband or vestigial sideband. These are forms that are used to improve on the amplitude modulated signal with carrier. And so you just need to be aware that they exist, and we discussed them, I think, in detail in the notes. You can read for yourself for understanding, not for the exam. The exam, let me worry about the exam. So I want you to understand things. Not for the exam. If you pay attention, you do assignments and so on, all of you, however many you are, should be able to get A's. Hope that can give you some comfort. Somebody can look at complicated things and then they'll say, "Is he going to require us to remember all these things?" And I don't do that. All right. So we now want to do some analysis on the AM signals, and we'll start off by saying that the power in an AM signal, I think this is, the power in an AM signal, if you have an AM signal which has got a carrier, so what will happen is that if you wrote the AM signal in the form, the one with the carrier, then you'll find that the sideband power, because the two components, the sideband power is given by m squared AC squared over 8 for one sideband, and the same for the other sideband. So you're going to get m squared AC squared over 4. AC is the amplitude of the carrier, and m is the modulation index. The carrier power, and I hope you know this, PC is AC squared over 2. You know that the power in the average power in a sine wave is the half of the amplitude squared. I hope that doesn't need to be derived. But you can derive it if you're given a sine wave, and you do it over one period, and you'll be able to just square the signal and divide by the period, and you integrate, then you'll get the amplitude squared over 2. The modulation index, the modulation efficiency, now not the index, the modulation efficiency is supposed to be useful power over total power. What do we mean by useful power? It is the power that is carrying the message. That is the useful power. Power that is used to carry the message is the power in the sidebands, because that's where the message is. And the total power is the sum of everything, the the message plus the carrier. And so when you do that, then you're going to take the the power in this modulation efficiency to be the power in the sidebands, which we found to be m squared ac squared over 4. And on the bottom, you're going to have the total power as the carrier power plus the power in the sidebands. The whole thing becomes m squared over 2 plus m squared. Now here is the kicker, as some people would like to say, that the maximum value, if you plotted this thing, because before we draw conclusions, if you plotted this thing, you'll find that it will be monotonically increasing. It starts off when m equals 0, it starts off at 0, and as m increases, it increases, but it increases at a decreasing rate. So that if you were to push this m to infinity, it will become 1. But we're not going to infinity. You'll find that if you take the derivative of this with respect to m, you'll find that the derivative, I think, has got 1 sign. Is it? Yeah. The second derivative is negative. You can try that, and but nonetheless, if you plotted this, you'll find that in the range from 0 to 1, or 0 to 1 of what? When m goes from 0 to 1, that this thing increases towards a maximum value, and the maximum value, when you allow the modulation index to go up to 1, is 1/3. When m equals 1, you get 1/3. So that's the best that you can do when you have amplitude modulation with the carrier. And by the way, some people call it amplitude modulation large carrier. So you can see in the text that's below that, we have LC, or large carrier. The efficiency cannot exceed 33%. If you had suppressed carrier, the efficiency is 100%. Well, that's a good thing. You'd prefer to have, because all the power is the power that is used is carrying the message. So the suppressed carrier would have 100% efficiency in terms of modulation efficiency. So what happens then is that you pay the price of that by having a more complicated circuit. So now we have what are called practical AM modulators. The AM has become more or less a word by itself. So even though the M in AM is modulation, or modulator, we can talk about AM modulator. And later on, we'll be talking about FM modulator, even though the M there again is modulation. So it's like we're repeating ourselves, but in this business, it's understood. Okay, one challenge in practical implementation is that it is difficult to implement an AM modulator without giving rise to unwanted sidebands. So we're trying to think about how to generate. By the way, before I go there, are there any questions? Silence. All right. So it is difficult to get a practical AM modulator. Remember, when we're producing the AM signals, we showed that you can just multiply two signals together. That is possible in principle, but in practice, what is done is not really a direct multiplication, because there are problems with those multipliers. So you can achieve that multiplication and even addition of the carrier by doing different things, by doing some clever tricks. So if you try to get an AM signal using practical implementations, there are usually some unwanted sidebands that end up coming. Your intention is to produce, let's say, the message M of t multiplied by the carrier. But when you're done, you look at the output and you'll find that instead of the M of t being multiplied by the carrier only, you'll find that M of t is multiplied by the carrier, perhaps something is squared, other terms come in. So one of the approaches then is to use different configurations, and one way is to use what is called a switching modulator. Here the diode comes again, but we're now going to use it to do different things. We have a switching modulator. So here the diode is being used. Again, it's a figure with no caption. But the diode is being used to switch on and off when the signal is when the input, in this case I think it's V1. When V1 is positive, the diode is on, and when V1 is negative, the diode will be off. So it's switching, and we are assuming an ideal diode. We are going to do some analysis to show that we can get our AM signal from this by selecting properly. I think we'll have to put some low pass filter in the system. But let's see what you have at the input of the diode. V1 is a sum of the message signal M of t and the carrier. So you have that sum at the input, and we will say approximately what happens is that the output V2 is approximately equal to V1 when the carrier signal is positive, and it is equal to 0 when the carrier is negative. Our assumption is that the carrier is larger, is much larger than M of t. So when the carrier is positive, that the input to the diode is positive, and when the carrier is negative, then the input to the diode is negative. So we're making that assumption. So if that's not the case, you just select the amplitude AC sufficiently to make this the case. So V2 is equal to V1 when the carrier is positive, and is equal to 0 when the carrier is negative. What this is saying is like you are having a square wave that is switching on at the rate of the carrier, so that when okay, the diagram is down here. You have a square wave here, we're calling GT sub 0, that is switching on when the carrier is positive, and it stays on for half the cycle. Then the other half it is 0, and so on. So what is happening is that these expressions that we've got here, V2 equals V1 when SCT is 0, sorry, is positive, and 0 otherwise. That is equivalent to, I hope you can see the expression in the middle here, where we're saying V2 is approximately equal to the input. The input V1 is the carrier plus the message. The carrier plus the message in the middle of the screen, multiplied by GT0. GT0 is a square wave that is on for half the time, half the period, and off the rest of the time. And the period we are calling T0. So now, if this is the case, then we can do some. We can get the Fourier series representation of the square wave, and the exercise that follows here, we are trying to get the Fourier series, and where we're saying GT0 has got a Fourier series, A0/2 plus that sum that we've got there. And so the calculations here that you have in the box, some of them circled in red, are to get for us the A's and the B's. It's a square wave and it is symmetric about the time axis. So you are going to find that the BNs in the Fourier series, my hope is that you are familiar with the Fourier series. If somebody is having a problem with that, please let me know. But you can also read the notes when I give them to you. They are, the earlier part of the notes talks about Fourier series in detail. But certainly the Fourier series of a square wave, I'm hoping that people will be familiar with. And if not, let me know. So this calculation here is basically just to get the ANs and the BNs. Somewhere we've shown in the bottom left, we've shown that BN is 0, B sub n is 0, and we get A0/2 is a half, and the other ones are given there. So I don't want to spend time on this. I'm hoping that you can read what is presented there. So what we are calling the gated signal is GT, that GT0T, now written fully in terms of its Fourier series, is got a half. And by the way, the half you could actually get without even doing integration, because it's the average value of the signal. Look, when you look at this signal that is in the middle, so it's not really the middle. Yeah, this signal, let's say at the bottom of the page, it goes to 1. It's 1 for half of the time, and then the other half it is 0. So if you take any cycle, its average is a half. Its peak divided by 2, and that is in the Fourier analysis. That is the first term that you're going to get. So if somehow somebody gave you a signal like that and you asked to write its Fourier series, you could get that half without even doing integration. But nonetheless, if you do the integration, you'll find that it is a half. So that so-called gating function is given by that expression there. So you can play with the n's, with the n, and you find when n equals 1, you have the first carrier frequency, a cosine of 2 pi fct, multiplying 2 over pi, because when n equals 1, yeah, and so on. So if you try to get the signal V2, which is the output, in case you have forgotten, we are trying to get an AM signal out of this mess. So what happens is that you can select from this multiplication, I think, by choosing just m equals 1. Yeah, sorry, n, the index in the summation equal 1, and you can say that is the desired component. Whatever you get from there is a desired component. In other words, you're going to get something, a constant plus a multiple of m of t multiplied by the cos 2 pi fct. There are other terms that will be at higher frequencies, n equals 2, n equals 3, and so forth. Those are going to have higher frequencies. So those can be removed by a low-pass filter. So what we are saying, it contains delta function. Well, we are calling this delta functions. The delta functions are just where the carrier frequency is in the frequency domain. And so we are using a trick where we're using the diode here as a switching device. And in the switching process, we are able to get an AM modulated signal. After some time, you will have forgotten what the steps are, and so what needs to remain when you have forgotten that, so that you will be requiring to look at the notes to see where this has come from. You'll know that we used a diode as a switching device, multiply the message signal, the message is added to the carrier. You have the message plus the carrier, and then you pass that through a diode. And if you pass that through a low-pass filter, you'll be able, by adjusting things properly, you'll be able to get an AM signal. That is possible to remember. But the details that you're having here, even after this, you probably won't remember. You need to get a piece of paper and start calculating them. Again, not to be memorized, because these things you memorize, but when you question yourself, maybe 3 or so months from now, you'll have forgotten. But what you should remember is that one way of generating an AM signal is by taking the AM signal, the message, adding to a carrier, passing the thing through a diode, and following that with a low pass filter. Let me see. I think I should have. I'm showing the spectral components here. I'm basically going very fast. I was hoping that yeah, here we go. So in this diagram, we have the full. I said a band. I think I said a low pass filter. All right, it's. I take that back. It's a band pass filter. Beg your pardon. I said low pass. I mean, I should have said band pass, because there are some components. Yeah, you want to retain M of t and M. Yeah, so it's a bandpass filter, all right, which has got a center frequency Fc and a bandwidth 2W, where W is the message bandwidth. Okay, so you are generating the signal that you want plus other components that you're going to throw off. So this is the diagram, and what we've done is just to explain its working. The other one is called a ring modulator, and I'm wondering whether to go through with this, because I have an exam in this same course that is going on, and some supplementary exam that supposed to be invigilating. I told the people to get started so that I'll join them later. So I want to pause here, and I'll give you some work later on, so that you can get yourself busy with these things in your spare time. So I want to pause there. There's in the next 7 minutes I should be stopping. So if there are questions, let me hear them, or other concerns. Silence. Alan, any question? There are two Alans. Andrew?
No. Yes. Where are the links for this class usually sent?
Where are?
The links. Where do you send the links? So
let me increase the volume. Okay, say it again.
I was having a problem getting
Yeah.
the link to the class. So where do you send
you're having a problem getting the link
to the class?
This
To
class.
the class. Yes.
The link to this class, or to the class, so that you can. No, not yet. I'm not set it. You'll. I think I'll do it later in the day, so that you can get everything you want from there. So I sent the message to that effect. You are a cluster. So that in the course of the day, I think it will be done.
Okay.
Okay.
No.
Yeah. So, anybody else? All right. I think we'll pause there, ladies and gentlemen. Then I'm going to stop it here.